Hello everyone, this is Saurabh from Edureka and welcome to today's session on deep learning tutorial with TensorFlow. So let us move forward and have a look at the agenda for today. So this is the agenda for today, guys. We'll understand what exactly is deep learning and how it works. So we'll look at the motivation behind deep learning and how it actually evolved. Then we'll focus on single layer perceptron, which are nothing but the early deep learning models. We'll also look at various examples of single layer perceptron. And guys, when I talk about perceptron, these are nothing but the artificial neurons. And what are neurons? Neurons are your brain cells. Then we'll also understand the limitations of single layer perceptron that led to the evolution of multi-layer perceptron. We'll understand how multi-layer perceptron overcame those limitations, and we'll also look at various examples of multi-layer perceptron. So guys, we'll move forward now and understand what exactly is deep learning and how it works. So guys, let us understand deep learning with an analogy. So how do you think our brain is able to identify the difference between a dog and a cat? So the reason is, since the day we are born, we are actually seeing different types of cats and dogs in our day-to-day life. And because of that, we are able to identify the difference or spot the difference between the two, that is dog and a cat. Even if we see different types of cats and dogs, we still know which is a cat and which is a dog. So this is because we have seen a lot of cats and dogs in our entire life. But what if I want a machine to do that task for me? So how will a machine identify whether the given image is of a dog or a cat? So one way of doing that is we can train our machine to a lot of images of different cats and dogs, that is different breeds of cats and dogs. And then what will happen once our training is done, we can provide it with an input image. Then we'll manually extract certain features. Features like nose, whiskers, colors, edges, it can be anything. The important features which actually helps us in classifying whether the input image is a cat or a dog. Then we make a machine learning model with that. And once it is done, our machine learning model is able to predict whether the input image is of a cat or a dog. But if you notice here, one very big disadvantage with this is we have to manually extract features. Features such as nose, whiskers, all those features we have to manually extract it and provide it to our machine learning model. And trust me guys, in every scenario it is not possible. If you have large number of inputs, you cannot do that. You cannot manually extract the features, or basically you can say columns which are important for you in order to predict what the object is, right? And that led to the evolution of deep learning. So what happens in deep learning? We skip the manual step of feature extraction. So what we do, we directly take the input image and feed it to our deep learning algorithm. And because of that, what happens, whatever features are we already manually provided, apart from that, there might be many other features which are important. For example, if our features don't include the length of the neck, and that is one of the major features in order to identify or classify whether it is a cat or a dog. Now what will happen, our algorithm will automatically determine that feature and will take into consideration, and then it will classify whether the input image is a cat or a dog. So what happens here, we provide an input image of a dog, and then it will automatically learn certain features even if we don't provide it with those features. And after that, it will give us the probability. And according to this particular scenario, it says 95% chances of being a dog, 3% chances of some other animal, similarly 2% chances of some other animal. So since the highest probability goes with the dog, so the prediction says that the object or the input image is nothing but a dog. Fine guys, so we'll move forward and we'll understand how exactly deep learning works. So the motivation behind deep learning is nothing but the human brain. As we have seen in the previous analogy as well, what we are trying to do, we are trying to mimic the human brain. We are trying to mimic the way we think, the way we take decisions, the way we solve problems. We are trying to make sure that we have a system that can mimic our own brain. So obviously the motivation for deep learning has to be our brain, and how our brain works with the help of our brain cells, which we call neuron. Now let us understand how a neuron works. And let me tell you guys, this is what we think how a neuron works. This is what our studies tell us. So yeah, so these are called dendrites. So dendrites receive signals from other neurons, and then it passes those signals to the cell body. Now this cell body is where we perform certain function. It can be a sigma function. That's what we believe. We believe it performs a sigma function. That is nothing but sums all the inputs. Then through axon, what happens? These signals are fired to the next neuron. And the next neuron is present at some distance, and that distance is nothing but synapse. So it fires only when the signals coming from the cell body exceeds a particular limit. Then only the cell or this neuron will fire the signals to the next neuron. And this is how the neuron or the brain cell works. and we take the same process forward and we try to create artificial neurons. So let us understand why we need artificial neurons with an example. So I have a data set of flowers, say, and that data set includes sepal length, sepal width, petal length, and petal width. Now what I want to do, I want to classify the type of flower on the basis of this data set. Now there are two options. Either I can do it manually. I can look at the flower manually and determine by its color or any means, and I can identify what sort of a flower it is. Or I can train a machine to do that. Now let me tell you the problem with doing this process manually. First of all, there might be millions of inputs that will be given to you. And for a human brain to perform that particular task is next to impossible. And at the same time, we always get tired at some point of time, right? So we cannot just continue working for a long period of time in single stretch. And the third point is human error risk, which is always there. So these are a few limitations with the human brain. So what we can do, we can train a machine to do that task for us, or we can put our brain inside a machine so that it can classify the flowers for us. So with this, what will happen? The machine will never get tired and it will make better predictions as well. So this is why we create artificial neurons, so that there's a system present that can mimic our brain. And this is what exactly happens. So this particular artificial neuron can actually classify the flowers, or you can say can divide the flowers on the basis of certain features. In our case, it is sepal length, sepal width, petal length, and petal width. So on that basis, it can classify the two flowers. So what we need here, we need some sort of a system that can actually separate the two species. And what is that system? Is nothing but an artificial neuron. So we need artificial neuron, and one type of artificial neuron is a perceptron. Now let me explain you perceptron with the flow diagram that is there in front of your screen. Now over here what happens, we have set of inputs like x1, x2, dash, dash, dash till xf. Now these inputs will be multiplied with their corresponding weights, which is w1, w2, w3 till wn in our case. Now these weights actually define how important our input is. So if the value of weight is high, we know that this particular input is very, very important for us. After multiplication, all of these are summed together and then it is fed to an activation function. Now, the reason of using activation function is to provide a threshold value. So if our signal is above that threshold value, our neuron, or you can say our perceptron, will fire. Else it won't fire. So that is the reason why we use an activation function. There can be different types of activation function. There can be sigmoid, there can be step function, sine function. Depending on our use case, we define the activation function. Now, the main idea was to define an algorithm in order to learn the values of the weights, which are W1, W2, W3 in our case, to learn the values of the weights that are then multiplied with the input features in order to make a decision whether a neuron fires or not. In context of pattern classification, which is in our case flowers, so we are trying to classify the two species of flowers, such an algorithm could be useful to determine if a sample belongs to one class or one type of a species or another class or another type of the flower. We can even call perceptron as a single layer binary linear classifier, to be more specific, because it is able to classify inputs which are linearly separable. And our main task here is to predict to which of the two possible categories a certain data point belongs based on a set of input variables. Now there's an algorithm on which it works, so let me explain you that. So the first thing we do is we initialize the weights and the threshold. Now these weights can actually be a small number or a random number, and it can even be 0. So it depends on the use case that we have. Then what we do, we provide the input and then we calculate the output. Now when we are training our model or we are training our artificial neuron, we have the output values for a particular set of inputs. So we know the output value. But what we do, we give the input and we see what will be the output of our particular neuron. And accordingly, we need to update the weights in order to reduce the loss, or you can say in order to reduce the difference between the actual output and the desired output. So what happens, let me tell you that. So we need to update the weights. So how we are going to update the weights is, we can say the new weight is equal to the old weight plus the learning rate. Learning rate, we'll discuss about it later in the session. But generally we choose learning rate somewhere between 0.5 to 0.01. After that, what happens, we find the difference between the desired output and the actual output. And then we multiply it with the input. So on that basis, we get a new weight. So this is how we update the weights. And then what happens, we repeat the steps 2 and 3. So we are going to repeat the steps 2 and 3. That is, we are going to apply this new weight. Again, we are going to calculate the output. Again, we are going to compare it with the desired output. And if it matches, then it's fine. Otherwise, we are going to update it again. So this is how the whole perceptron learning algorithm works. And don't worry guys, I'm going to show it to you practically how it actually works in my PyCharm. Fine guys, so we'll move forward and we'll see the various types of activation functions. So these are the various types of activation functions that we use, although there can be many more activation functions. Again, I'm telling it depends on your use case. So we have a step function. So if our output is actually above this particular value, then only our neuron will fire, or you can say the output will be +1. Or if it's less than this particular value, then we'll have no output, or we'll say 0 output. Similarly for the sigmoid function as well, and same goes for sine function. Now, as I've told you earlier as well, it can be used to classify any linearly separable set of inputs. Now, let me explain to you with the diagram that is there in front of your screen. So we have different types of dogs and we have horses. And we want a line that can separate these two. So our first iteration will produce this sort of a line. But here we can notice that we have error here, as we have classified one of the horses as a dog and a dog as a horse. So error is 2 here. Similarly, what happens, we have updated the weights. Now after updating the weight, what happens, our error has reduced. So what happens now, we have actually classified all the horses correctly, but one dog we have classified wrong and we have considered it as a horse. So our error becomes 1. Once again, what will happen, if you can remember, the step 2 and 3 of our perceptron learning algorithm will be done. And then after that, our weights will be updated and our desired output will become equal to our actual output, and we get a line something like this. So what we have now, we have properly classified dogs and horses. So this line separates both of them. This is how we can actually use a single layer perceptron in order to classify any linearly separable set of inputs. Now we can even use it in order to implement a logic gates, that is OR and AND. Now let me tell you how you can do that. First we'll look at OR gate. Now in OR gate, what happens here is the truth table. Truth table, according to that, we have two inputs, x1 and x2. So if both are 0, we get a 0. If any one of the input is high or any one of the input is 1, we get the output as 1. So what we need to do is we need to make sure that our weights are present in such a way that we get the same output. So how we have done that, when the value of weight is equal to 1, and then we provide the input x1 and x2, after passing through this activation function, we get this sort of a graph, which is the graph for our OR gate. Now if you want, I could use a pen and I can explain it to you. Now we have x1 and x2 as inputs. So we provide first input as 0, x1, and this also as 0. So 0 into 0 is again 0, 0 into 0 is 0. And then we pass it through this activation function. Now we need to make sure that whatever value that comes here should be greater than 0.5, then only our neuron or the perceptron will fire. But since this value is actually less than 0.5, so the neuron won't fire and our output will be 0, as you can see it over here. Now let's take the other set of inputs. Now our x1 is 0 and our x2 is 1. So 1 into 1 will be obviously 1. Now in this case, our output is bigger than 0.5. Then what will happen? Our neuron will fire and will get 1, the output 1 here, as you can see it in the graph. Similarly, when my x1 is 1 and x2 is 0, in that case also, our output is greater than 0.5, our neuron will fire and will get this sort of a graph. When I talk about 1, 1, then our output will be 2, which is greater than 0.5. So we get an output that is 1. And this is how we get the graph. So this is how we get this graph. And now if you notice, with the help of the single layer perceptron, we are able to classify the 1s and 0s. So this line, anything above this line is actually 1. And anything below this line, we have 0s. So this is how we are able to classify or able to implement OR gate. Similarly, when I talk about AND gate as well, so there's a difference in the truth table of AND gate. In AND gate, what happens? We need to make sure that both of our inputs are high in order to get a high output. If any of the input is low, we get a low output. And that's the reason we choose an activation function that is 1.5, which means that if our value or the output is above 1.5, then only our neuron will fire and we'll get 1 here. And there is only one case, that is when both the inputs are high. So when both the inputs are high, let me just use my pen again and I'll explain to you. So x1 is 1. x2 is 1, we get something which is 2, which is obviously greater than 0.5. Pardon me for my writing, but yeah, this is how it is. Yeah. So 1 plus 1, 2, which is obviously greater than 0.5. So what we get, our neuron fires and we get 1 here. But for the rest of the inputs, all will be less than 1.5. So that is why our neuron doesn't fire and we get a 0 output. Don't worry guys, I'll actually tell you how to implement it. I'll open my PyCharm and I'll be showing it to you practically how to implement these gates. So for that, what I'm going to do is I'm going to first import a Python library called TensorFlow. The installation guide of this particular library is present in an LMS for both Windows as well as for Linux. So you can just go through it and it's very easy to install that. And I'll actually execute this practically later in the session. You don't need to worry about it. So this is how we can implement and OR gate. So let's move forward, guys, and we'll actually understand with a use case that is of MNIST dataset. The reason for using MNIST dataset is because it is already clean and will be a perfect example for this. Now what this MNIST dataset contains, it basically contains handwritten digits from 0 to 9, and in that dataset we have 50,000 training images along with 10,000 testing images. So we will train our model with those 55,000 training images, and then we are going to test the accuracy of a model with the help of those 10,000 testing images. And for all of this, we need to understand first what exactly is TensorFlow. So let us move forward, guys, and we'll understand TensorFlow, and then we are going to implement all these things that we have discussed, that is AND gate, OR gate, and the MNIST dataset that I'm talking about. So let's move forward, guys, and understand what exactly is TensorFlow. Now what is TensorFlow? As I've told you earlier as well, we use this TensorFlow library in order to implement deep learning models. And the way the data is represented in the deep learning model is called tensors. Now what are tensors? Now tensors are just the multi-dimensional arrays, or you can say an extension of two-dimensional tables, matrices, to data with higher dimension. Now let me explain to you with the examples that are there in front of your screen. So this particular data is nothing but a tensor of dimension 6, because we have 6 rows and we have only one single column. Now over here we have 4 columns as well as 6 rows, so this becomes a tensor of dimension 6, 4. Similarly over here as well, so we have another dimension, that is the third dimension, in which we have 2 values, so we consider this as a tensor of dimension 6, 4 and 2. So this is nothing but a way of representing data in TensorFlow. Now if you consider the TensorFlow library, at its core it is nothing but a library that performs matrix manipulation. That is what TensorFlow is. Now let us move forward and understand TensorFlow in a bit detail. So as the name tells that it consists of 2 words, tensor as well as flow. Now we understood what exactly tensor is. We saw it in the previous slide as well. Now when I talk about flow, it is nothing but a data flow graph. So let me just give you an example that is there in front of your screen. So we talked about weights and inputs. So we provide these weights and inputs and we perform a matrix multiplication. So weight is one tensor, X input is one tensor, then we perform matrix multiplication. After that we add a bias, which we'll actually see it later in the session. You don't need to worry about this term. Then what we do, we add all of these. So what is this? This is nothing but the sigma function in the perceptron that we have seen. Then we pass it through an activation function, and the name of that activation function is RELU or RELU, what you can say it, and then a neuron will fire. So this is nothing but a flow, or you can say a data flow graph. Now let us understand few code basics of TensorFlow. Now the TensorFlow programs actually consist of 2 parts. One is building a computational graph and another is running a computational graph. So we'll first understand how to build a computational graph. Now you can think of a computational graph as a network of nodes, and with each node known as an operation and running some function that can be as simple as addition or subtraction, or it can be as complex as, say, some multivariate equation. Now let me explain it to you with the code that is there in front of your screen. So the first thing you do, you import the TensorFlow library. Then what you do, you define 2 nodes, and these nodes are constants. So we'll call that function, we'll call it as tf.constant, and we'll provide a value that is 3, and it is nothing but a float number of 32 bits. Similarly, we defined one more node, which is a constant, and it contains value 4. So these are nothing but your constant nodes. So this is basically what computational graph is. So basically we have built a computational graph, and in this graph each node takes 0 or more tensors as inputs and produces a tensor as an output. And one type of node is a constant that I've told you earlier as well. And these TensorFlow constants, it takes no inputs and it outputs a value which is stored internally. Now what I'll do, I'll actually execute this in my PyCharm. So for that I'll open it. So this is my PyCharm, guys, and I've already installed TensorFlow. So the first thing that I need to do is import the TensorFlow library. For that I'm going to type in here import TensorFlow as TF. So if you're familiar with the Python basics, you know what it means actually. So I'm importing TensorFlow library, and in order to call that, I'm going to use the word TF. So after that, I'm going to define my node 1 and node 2, which are constant nodes. So for that, I'm going to type in here node 1 equal to tf dot constant, and then I'm going to define the constant value in this. So it'll be 3, and it'll be a float value of tf dot float of 32-bit. All right. And now I'm going to define my second constant node. So I'll type in here node 2 tf dot constant. I'll put 4 in here and 4. That's it. And so the tf.float 32 will be present implicitly. I don't need to do that again and again. So I have created a computational graph here. So what if I print it now? So let us see what will be the output. Node 1 comma node 2. Let's go ahead and run this and see what happens. If you notice here that printing the nodes does not output the values 3 and 4. You might be expecting that, right? That it should print 3 and 4. But instead they are nodes that when evaluated would produce 3 and 4 respectively. So to actually evaluate the nodes, what we need to do is we need to run this computational graph. So let me show you that. For that, I'm again going to open the slides. So since I've told you earlier as well, we need to actually run this computational graph within a session. And what is this session? Its session actually encapsulates the control and state of the TensorFlow runtime. Now the code that is there in front of your screen, what it will do, it will actually create a session object, and then it invokes its run method to run enough of the computational graph in order to evaluate node 1 and node 2. And how it does that? By running the computational graph in a session. So now let me show it to you practically how it happens. So again, I'm going to open my PyCharm. This is my PyCharm, guys. So let me first comment this print statement, and now I'm going to run a session. So for that, I'm going to type in here ses equal to tf dot session, and now I'm going to print it. So for that, I'm going to type in print ses dot run, and what I want to run, I want to run node 1 and node 2. So I'm going to type in here node 1 comma node 2. That's all. And now when I run this, it will actually give me the value 3 and 4. And yup, it does. It gives me the value 3 and 4. So what we did, we first built a computational graph. We first saw how to build basically a computational graph. And then we understood that these all are nodes. So in order to get their value, we need to evaluate those nodes, and how we can do that by running the computational graph inside a session. And when finally, when we run that session, we get the output 3 and 4, which is nothing but the values of those nodes. And the one thing that you must have noticed here is that it will always produce a constant result, right? So how to actually avoid that? So we saw how to run a computational graph as well. Now let me explain it to you with one more example. So this is one example in which we take 3 constant nodes A, B, and C, and we perform certain operations like multiplication, addition, and subtraction. And then we run the session, and then we finally close it. And this is the diagram how it looks like. So we have 3 constant nodes, C, B, A. A contains value 5, B contains 2, similarly C contains 3. So first we add C and B, then we add B and A. Then we get 2 other nodes, that is E and D. And then from that E and D, what we are going to do is we are going to subtract both of them, and then we get the final output. Now let me go ahead and execute this practically in my PyCharm. So this is my PyCharm again, guys. First thing I need to do is import TensorFlow as TF. Then we are going to define the 3 constant nodes. So first is A equals to TF dot constant, and the value that will be there in A will be 5. Then I'm going to define one more constant node, that will be B TF dot constant, and the value that will be there in it will be 2. And then I'm going to define the last constant node, and TF dot constant, the value that will be there is 3. All right, so we have 3 constant nodes, and now we are going to perform certain operations on them. For that, I'm going to define one node, let be D, which will be equal to TF dot multiply. So the 2 nodes that we want to multiply, so that'll be A comma B. And then there'll be one more node in order to perform some operation, that is addition. So TF dot add C and B. And then we're going to define one more node, let be F, and inside that node we're going to perform the subtraction operation, TF dot subtract D and E. So we have built a computational graph. Now we need to run it, and you know the process of doing that. Ses is equals to tf.session. Then we are going to define a variable, let it be outs, outs, whatever name that you want to give in, and just type in a ses dot run f. Let's see if that happens or not. And then we're going to print it. So for that, I'm going to type in here print out. Let's go ahead and run this and see what happens. So we have got the value 5, which is correct, because if you notice our presentation as well, let me open it for you. Over here, we get the value 5, similar to our implementation in PyCharm as well. So this is how you can actually build a computational graph and run a computational graph. I've given you an example. Now guys, let us move forward, because these are all the constant nodes. What if I want to change the value that is there in the node? So for that, we don't use the constant nodes. For that, we use placeholders and variables. Let me explain it to you. First, I'll open my slides. So since these are all constant nodes, we cannot perform any operation. Once we have provided a value, it will remain constant. So basically, a graph can be parameterized except external inputs as well. And what are these? These are nothing but your placeholders. And these placeholders is basically a promise to provide values later. So there's an example that is there in front of your screen. Over here, these 3 lines are bit like a function or a lambda in which we define 2 input parameters A and B, and then an operation possible on them. So we are actually performing addition. So we can evaluate this graph with multiple inputs by using feed_dict parameter. As you can see, we are doing it here. So we are actually passing all these values to our placeholders here. So these all values will be passed, and accordingly we'll get the output. So let me show you practically how it happens. So I'm going to open my PyCharm once more. I'll remove all of this, and yeah. So the first placeholder, I'm going to name it as A, tf dot placeholder, and what sort of a placeholder it'll be, so I'll consider it as float number of 32 bits. Similarly, I'm going to define one more variable as well, and I'm going to name it as B. Then I'm going to define an operation that I'm going to perform on them. So I'm just going to type in here adder underscore node equals to A plus B. And now our placeholders are currently empty. So as I told you earlier as well, placeholders are nothing but a promise in order to feed values later. So this is how we have built a computational graph. Now our next step is to start a session. So for that, I'm going to type in a ses equals to tf dot session. Right. Since these placeholders are currently empty, and we know that these placeholders are nothing but a promise in order to provide them with certain values later. So let's go ahead and provide the values, or you can say a list of values. So I'm going to type in here print ses dot run adder underscore node. And then the values that I'm going to feed in. So basically I'm going to feed in a dictionary, a colon 3, a colon a list of integer values between 1 to 3, and one more will be B colon a list of integer values between 2 and 4. All right, so this is done. Now let us go ahead and execute this and see what happens. So we have got the output 3 and 7. So basically if you add 1 and 2, you get 3. Similarly, you add 3 and 4, you get 7. It's pretty easy mathematics, but my main focus was to make sure that you understand what are placeholders. So we understood what exactly are placeholders. Now it's the time to understand what are variables. So basically in deep learning, we typically want a model that can take arbitrary inputs. Now in order to make the model trainable, we need to able to modify the graph to get new outputs with the same input. And what helps us to do that? Variables basically allows us to add trainable parameters to our graph. So in order to declare variables, what we do is, you can refer the code that is there in front of your screen. So we have taken 2 variables and 1 placeholder, and the first variable has a value 0.3, the another variable has minus 0.3, and the placeholder, obviously it will remain empty, and then later on we feed in some values to it. Then we create a linear model, or you can say some operation in which we are going to multiply this W with X, and then we are going to add a bias or a B value to it. Then what we need to do is we need to initialize all the variables in the TensorFlow program. So for that, you must explicitly call a special operation, which is a tf.global variable initializer, and then just directly run the session. Now let us go ahead and execute this practically, guys. Let me remove all of this. Yeah. So our first variable will be w, and we are going to call in tf.variable. And in that variable, we are going to store a value which is 0.3. And it is of a float type 32-bit. So just type in here tf.float 32. Yeah. Then we're going to define one more variable, let it be b. So I'm going to type in here tf.variable, and the value of this variable will be minus of 0.3. Again, it is float type of 32-bit. So just type in that tf.float 32. Now I'm going to define a placeholder, that is x. X is equals to tf dot placeholder, and it is again a float type 32-bit. And then some operation that we are going to perform. So I'm going to type in here linear underscore model equal to w multiplied by our x value, that is a placeholder, and then we want to add bias to it or b value to it. All right. Now, as we have seen earlier as well, in order to initialize constants, we call tf.constant, and their value will never change. But by contrast, variables are not initialized when you call tf.variable. So to initialize all the variables in the TensorFlow program, what you need to do is you need to explicitly call a special operation. And how you're going to do it, just type in here init equal to tf.global underscore variables underscore initializer. That's all. And then we're going to run a session. So you know the process. Ses is equals to tf.session init. Now let's print it, and before that what we need to do is we need to provide the x placeholder with some values. We're actually going to do that in the print statement itself. So I'm going to type it ses.run what? Run a linear model. And the values that we are going to pass in x will be a dictionary again, and let me show you how you can do that. So x colon, and it'll be a list of values from 1, 2, 3, 4. Yeah, that's all. And we are going to run it now. So this is how we get the output. It's simple mathematics. What we have, the first value of w will be 0.3, and the first value of a b will be a minus 0.3, and the first value of x will be 1. So it'll be 3 minus 3, which is again 0. Similarly, for other values as well, you can calculate it. It's absolutely correct. So what we have done, we have created a model, but we don't know how good it is yet. So let's see how we can actually evaluate that. For that, I'm again going to open my slides. So now in order to evaluate the model on the training data, we need a placeholder y, as you can see in front of your screen, to provide the desired values. And we need to write a loss function. So this placeholder y will actually be provided with the desired values for each set of inputs. And then we're going to calculate the loss function. And how are we going to do that? We're going to minus the actual output with the desired output, and then we're going to do the square of it. After that, we're going to sum all of these squared deltas, and then we're going to define one single scalar as loss. So this is how we are actually going to calculate the loss. And then after that, we need to provide the values to x and y placeholders. So what I'm going to do, I'm going to open my PyCharm, and then I'm going to show you how correct our model is on the basis of the values that we provide to y placeholder. So guys, this is my PyCharm again, and since here what I'm going to do is I'm going to define a placeholder first. Y is equals to tf.placeholder tf.float 32. So I'm going to type in a tf.float 32 square delta. I've explained you all these things, but yeah, I'm going to tell it to you again as well. Don't worry about it. tf.square the actual output minus the desired output, and then I'm going to sum all of those losses, or you can say square deltas. tf.reduce underscore sum. So I'm going to type in here square deltas. Then finally print it. So I'm going to type in ses.run loss x colon 1, 2, 3, 4. 0, minus 1, minus 2, minus 3. And that's all, and we are good to go. Let's run it and see what will be the loss. So the loss is 23.66, which is very, very bad. Now our next step is to realize how to actually reduce this loss. So let's go ahead with that. I'm going to open my slides once more. So in order to minimize the error, now in order to reduce this loss, TensorFlow provides optimizers that slowly change each variable in order to minimize the loss function. And the simplest optimizer is gradient descent. In order to do that, we have to call the function called tf.gradients. So as you can see it in the code itself, so we have a tf.train.gradient descent optimizer, and this is nothing but the learning rate 0.01. Then train equals to optimizer dot minimize the loss. So we're going to call this optimizer, which is nothing but the gradient descent optimizer, in order to minimize the loss. And then we are going to run it. So let's see if that happens or not. So for that, again, I'm going to open my PyCharm. And over here, let me first comment this print statement. And now I'm going to type in here optimizer equals to tf dot train gradient descent optimizer, and the learning rate will be 0.01. And guys, let me tell you, this is just an introductory session to TensorFlow and deep learning. So all the modules that we have discussed in the beginning will be covered in detail. So whatever topics are there in those modules will be covered in detail. So you don't need to worry about it. So I'm just giving you a general introduction and overview of how things work in TensorFlow. Now I'm going to type in here train equal to optimizer dot minimize loss. And then now let's go ahead and run this. Ses dot run init ses dot run, and we're going to feed in values to our x and y placeholders. Train comma x will have values 1, 2, 3, 4, and y will have values 0, comma minus 1, comma minus 2, comma minus 3. Print ses dot run w, comma p. Now let me first go ahead and comment these lines. All right. So I've just made a mistake here. This is in uppercase W, and yeah. So now we are good to go, and let's run this and see what happens. So these are our final model parameters. So the value of a W will be around 0.999969, and the value of our B will be around 0.9999082. So this is how we actually build a model, and then we evaluate how good it is, and then we try to optimize it in the best way possible. So I've just given you a general overview of how things works in TensorFlow. So now is the time to actually implement the AND and OR gate that I was talking about at the beginning of the session. So for that, let me first remove all of this. Yeah. Now in order to implement AND gate, our training data should consist of the truth table for AND gate. And we know that truth table, and we know that if any of the input is low, then the output will be low, and if both the inputs are high, then the output will be high. One thing to note here, guys, is that the bias is implemented by adding an extra value of 1 to all the training examples. So yeah, enough with the explanation. Let's go ahead and code it. So I'm going to type in here t comma f equal to 1 point comma minus 1 point. And bias will always be 1. So I'm going to type in here bias is equals to 1.0. And now I'm going to provide the training data. So for that, I'm going to type in train underscore in equal to, if one input is true and the another input is also true, then we have bias. Then again, if one input is true, the other input is false, then also we have bias. Similarly, one input is false, another input is true, then we have bias. And then finally, when both the inputs are false or 0, then we have bias, right? This is our training data. And the train out will type in here as the output basically, train underscore out will be equal to, so yeah, if both the inputs are true or both the inputs are 1, then the output is true. Oops, I forgot a comma everywhere. Let me just go ahead and do that. Yeah. So if both the inputs are true, the output will be true. If any of the input is false, the output will be false. So I'm just going to type in here false everywhere because there's only one condition in which we have the true output. All right, so this is done now. Now, as we know that TensorFlow works by building a model out of empty tensors, then plugging in known values and evaluating the model like we have done in the previous example. Since the training data that we have provided will remain constant, the only special TensorFlow object we have to worry about in this case is our 3x1 tensors of vectors. And now what we are going to do, we're going to define a variable and we are going to put in some random values in it. So I'm just going to type in tf.variable and generate the random function tf.random underscore normal 3,1. Now what it is basically a variable. So its value may be changed on each evaluation of the model as we train, with all values initialized to normally distributed random numbers. Now that we have our training data and weight tensor, we have everything needed to build our model using TensorFlow. So what we need to do, we need to define an activation function. And we are going to define a step activation function or step function. So for that, what I'm going to write here is a function step. We're going to define our own step function, although you can use the predefined function as well. That totally depends on you. I'm going to type in here is greater equal to tf dot greater x comma 0. Then we're going to define one more variable as float tf dot to underscore float is underscore greater. Then we're going to define one more variable, a doubled equal to tf dot multiply as underscore float comma 2. Then return tf dot subtract doubled comma 1. So now this is how we have defined our step function. So with the step function defined, the output error and the mean squared error of our model can be calculated in one short line each. Let me show you how you can do that. So just type in here output equal to, call that function that is step tf dot matrix multiplication matmul train underscore in comma w. Now for error, we're going to type in here error equals to tf dot subtract train underscore out comma output. And for mean squared error, I'm going to type in here MSC equal to tf dot reduce underscore mean tf dot square and then error. Now the evaluation of certain tensor functions can also update the values of variables like our tensor of weights w. So in our case, basically we're going to update the weights w. So first we calculate the desired adjustment based on error, then we add it to w. Now let me show you how we'll do that. So if you can recall, we have done that in the previous example as well, where we were updating the weights and biases. So now I'm going to type in here delta is equals to tf dot matmul, or you can say matrix multiplication train underscore in comma error comma transpose underscore a equals to true. Then we're going to type in here train equal to tf dot assign w comma tf dot add w comma delta. So first matrix multiplication and then we're going to add it all. The model has to be evaluated by TensorFlow session, which we have seen earlier as well. But before that, we also need to initialize all the variables. So first let me just type in here ses equals to tf dot session, and then I'm going to type in here ses dot run tf dot initialize underscore all variables. So now what our next task is, in order to perform various iterations so that we get zero error. So what we're going to do, we're going to define a variable ERR and our target. So basically our ERR is nothing but an error which can be equal to 1 or 0 because we are using binary output. So our error can be 1 and our target is to make it as 0, right? Now next what we're going to do, we're going to define epoch. Now you can consider right now epoch as nothing but the number of cycles, or you can say number of iterations that will be required in order to reach the desired output, or you can say in order to reduce the error to 0. So I'm just going to define that. So I'm going to type in here epoch, or you can give whatever variable name you want. And I'm going to type in here max underscore epoch equal to 0 comma 10, which means that it'll start from the 0th epoch and our maximum value of epoch will be 10. Now I'm going to define while ERR is greater than target and epoch is less than maximum epoch, increase the value of epoch y1. Then we're going to type in ERR ses.run mean squared error comma train, and let's just finally print it and see what happens. Print epoch mean squared error colon ERR. So basically what it'll print the cycles or epoch and the error with respect to that particular cycle. So let us go ahead and execute this and see what happens. Oops, I've typed the spelling of square wrong. Pardon me for that. So I'm just going to make it right now. SQUARE. All right, let's go ahead and execute it once more. So yeah, in 3 epochs, we got the value of mean squared error as 0. That means it took us 3 iterations in order to reduce the output to 0. So this is how you can actually implement a logic gate, or you can say this is how you can actually classify the high and low outputs of a particular logic gate using single layer perceptron. So what I'm going to do, I'm going to create a new Python file and I'm going to name it as MNIST, which is nothing but the data set on which we are going to perform the classification of handwritten digits. So we're going to execute a use case, and I've told you earlier as well, in this MNIST data set we have handwritten digits from 0 to 9, and it has 55,000 training sets as well as 10,000 test sets. So let us go ahead with that. So first thing I'm going to do is download the data set, but before that let me just import TensorFlow library as TF. And yeah, now let us download the data set. So for that I'm going to type in from tensorflow.examples.tutorial.mnist import input underscore data. And now I'm going to type in here MNIST is equals to input underscore data underscore data dot read datasets. Type in here MNIST underscore data comma 1 underscore hot equals to true. Now here MNIST is nothing but a lightweight class which stores the training, validation and testing sets as numpy arrays. And when I talk about this 1 hot equals to true is nothing but 1 hot encoding. Now let me tell you what 1 hot encoding is. So for that let me just comment a few lines. So 1 hot encoding means that if I'm classifying something as a 7, so if I classify that my digit is 7, so how am I going to represent that? So I'm going to type in here 0, 1, 2, 3, 4, 5, 6. 7th bit will be active, so I'm going to type in there 1, then 8, and then 9. Similarly, if I want to represent, say, that my digit is 2, so I'm going to type in 0, 1. On the second digit, I'm going to type in here as 1, and the rest all zeros. So I hope you got the concept of what exactly 1 hot encoding is. So it's like only one output is active at a time. That's all.
So our next step is to start the session like we do every time. So I'm going to type in here ses equals to tf dot interactive session. So I'm just going to type in here interactive session. Yeah. And now we are going to build the computation graph by creating nodes for the input images and target output classes. So for that, I'm going to define some placeholders. For that, I'm going to type in x is equals to tf dot placeholder tf dot float 32, and the shape will be none, 784. Now the input images x will consist of 2D tensors of floating point numbers. Here we assign it a shape of say none, 784 as you can see. So where 784 is the dimensionality of single flattened 28 by 28 pixel MNIST image of handwritten digits. And what none indicates, it indicates that the first dimension corresponding to the batch size can be of any size. Means the first dimension can be of any size. We are not putting any restrictions on that. Now I'm going to define variable y, which will be nothing but our real labels, or you can say the desired output. Placeholder, and I'm going to type in here tf dot float 32, and I'm going to define the shape, which will be none, 10 because we have 10 classes. And similarly, y is also a 2D array where each row is one hot 10-dimensional vector indicating which digit class the corresponding MNIST image belongs to. And now next step is to define weight and biases for our model like we have done in the previous example. So we could imagine treating these like additional inputs, but TensorFlow has even a better way to handle them, and what it is nothing but variables. So let us go ahead and do that. I'm going to type in here wtf dot variable tf dot zeros. I'm going to initialize it to zeros, and the shape will be a 784, 10. So it's like 28 cross 28 pixels and 10 classes. Similarly, when I talk about bias, so it'll be tf dot variable tf dot zeros, initialize it to zeros, and the shape will be 10. We pass the initial value for each parameter in the call to tf dot variable. Now over here, as we can see that we initialize both w and b as tensors full of zeros, and w is a 784 cross 10 matrix because we have 784 input features and 10 outputs. And when I talk about bias b, it is a 10-dimensional vector because we have 10 classes. And we have learned that before we can use variables in a session, we need to first initialize it. So we're going to type in here says a dot run, and after that I'm going to type in tf dot global underscore variables underscore initializer. Alright, so we have initialized all the variables. So our next task is to predict the class and the loss function. So we can now implement our regression model. It takes only one line. We multiply the vectorized input image x by the weight matrix w and add the bias. So for that, I'm just going to type in here y equal to tf dot matmul, that is nothing but matrix multiplication, x comma w plus b. All right. So now we can specify a loss function very easily. So the loss indicates how bad the model's prediction was on single example. We try to minimize that while training across all the examples. So now we can specify a loss function. Now loss indicates how bad the model's prediction was on a single example, and we try to minimize that while training across all the examples. Now here our loss function will be cross entropy, or you can say the difference between the actual output and the predicted output. So for that, what I'm going to do, I'm going to make use of softmax cross entropy function. So here the loss will be the difference between the target output and the actual output. So for that, what I'm going to do is I'm just going to type in here a variable name. I'm going to name it as cross entropy. And yeah, entropy equals to tf dot reduce underscore mean. And then just type in here, let me just enter the next line, tf dot nn dot softmax underscore cross entropy with logits. And now over here I'm going to type in first our target output, which will be labels equals to y, comma our actual output, so it'll be logits is equals to y. That's all. So over here, let me just give you a brief idea what is happening. So labels is equals to y means that this is our target output and this is the actual output. So we'll name it as y underscore. And so what exactly is happening? It will calculate the difference between the target output and for the actual output for all the examples. Then it is going to sum all of them and then find out the mean. So this is what basically this cross entropy variable will do. Now that we have defined our model and training loss function, it is straightforward to train using TensorFlow. Now we need to train our model. So TensorFlow has a wide variety of built-in optimization algorithms, as I've told you earlier as well. And for this example, we'll use steepest gradient descent with a length of about 0.5 to descend the cross entropy. So basically we're going to use a 0.5 learning rate, or you can say the step length. So for that I'm going to type in here train underscore step equal to tf.train dot gradient descent optimizer, and the step will be 0.5 and minimize the loss, so minimize cross entropy. That's it. So what this one line basically will do, it will minimize the cross entropy, which is nothing but the loss function that we have defined. Now in the next step, what we are going to do, we are going to load 100 training examples in each training iteration. So each time the training iteration happens, it will take 100 examples. We then run the train underscore step operation, which is nothing but to reduce the error, using feed underscore dict, which is nothing but we are going to feed the real values to our placeholder y. Now next what we are going to do, we're going to load 100 training examples in each training iterations, which means that for each iteration we'll take 100 training examples and we'll run the train underscore step operation, which is nothing but the optimizer here. And after that we are going to use a feed underscore dict to replace the placeholder tensors x and y with the training examples. So basically x will contain the input images and y will contain the actual outputs, or you can say the desired outputs. For that I'm going to type in here for underscore in range 1000 batch equals to MNIST dot train dot next underscore batch 100 train underscore step dot run, and I'm going to feed in the values to x and y variable. Feed underscore dict equal to x colon batch 0 comma y colon batch 1. That's it. Now we need to evaluate our model. We need to figure out how well our model is doing, and for that I'm going to make use of tf.argmax function. Now this tf.argmax function, let me tell you how it works. First I'm going to type in here correct underscore prediction equals to tf.equal tf.argmax y underscore comma 1 comma tf.argmax y comma 1. So basically this tf.argmax y underscore comma 1 is a label our model thinks is most likely for each input. That means it is our predicted value. While tf.argmax y comma 1 is a true label. It is there in our dataset present already, and we know that it is true. So what we are doing, we are using tf.equal function to check if our actual prediction matches the desired prediction. So this is how it is working. So now what we're going to do, we're going to calculate the accuracy to determine what fraction are correct. We cast a floating point numbers and then take the mean and repeat. So now I'm going to define a variable for accuracy. So just going to type in accuracy equals to tf.reduce underscore mean, tf.cast correct underscore prediction, comma tf.float 32. And what we can do finally, we can evaluate our accuracy on the test data. And this should give us accuracy of about 90%. So let us see if that happens. So I'm going to type in here print accuracy dot evaluate eval feed underscore dict equal to x colon MNIST dot test dot images comma y colon MNIST dot test dot labels. That's it, guys. And I've done a mistake here. Instead of y, it will be y underscore because this is our predicted value, not the actual value. And y we have considered as actual value. And this y underscore will be our predicted value. So this is the mistake that I made. So yeah, now I think the code looks pretty fine to me and we can go ahead and run this. Let us see what happens when we run this. So guys, it is complete now, and this is the accuracy of a model, which is 91.4%, and which is pretty bad when you talk about a data set like MNIST. But yeah, with a single layer, it is very, very good. So we have got an accuracy of around 92% on the MNIST data set, which means that whatever the test data sets were there, that is like 10,000 test images. So on those test images, whatever the prediction our model has made are 91.4% correct. So guys, let me just give you a quick recap of what all things we have discussed. So first we saw what exactly is deep learning and how it is different from the traditional machine learning. Then we understood the motivation behind deep learning, which is nothing but your brain cells, which are called neurons. Then we understood the importance of why we need artificial neurons. And then we took the example of artificial neuron, which is called a perceptron. And we looked at a couple of examples in which we implemented the AND gate. We performed image classification on the MNIST datasets, which is nothing but handwritten images between 0 to 9. And we also implemented a couple of examples in order to understand what are placeholders, variables, and constants. So now there are certain limitations of single layer perceptron. Let us understand that. So in order to understand that, we'll take an example and how can we implement XOR gate using single layer perceptron. So let us see if we can do that or not. So we have an XOR gate here and this is the truth table. So according to this truth table, if any one of the input is high, then the output is high. And if both the inputs are low, output is low. And if both the inputs are high, output is low. So how can you classify the high and the low outputs with a single line? Definitely you can't. If you see the points, so one point is here, one is here, here, and here, in which these 2 points are high outputs and these two are low. So how can you classify with a single line? Definitely you can't. So now what's the answer to this? What if we use multiple neurons? So using multiple neurons, we can have 2 lines that can separate it. Now we can solve this problem if we have multiple neurons. So if we use 2 neurons, we can have 2 lines and that can actually separate the high outputs as well as the low outputs. So this is where we use multi-layer perceptron with backpropagation. So what are multi-layer perceptron? Multi-layer perceptrons, they have the same structure like the single layer perceptron. The only difference is they have more than one hidden layer. So let me explain it to you with an example. So this is how a typical multi-layer perceptron looks like. So we have input layer, we have 2 hidden layers, and we have 1 output layer as well. Now typically each of these input layers are connected to the next hidden layer. Each neuron is connected to the next neuron present in the adjacent layer. But the neurons of the same layer are not connected to each other. Now what happens, a set of inputs are passed to these input layers and the output of this input layer will be passed to the first hidden layer. Then after activation function of the first hidden layer, the output will be passed to the next hidden layer as the input, and similarly finally we get the output. Now you must be thinking how the model learns from here. So basically the model learns by updating the weights, and the algorithm that it uses is called backpropagation. So the backpropagation algorithm helps the model to learn and update the weights in order to increase the efficiency. So basically this process of from input layer to the output layer is called a feed forward process. And then when we backpropagate it in order to increase the efficiency or accuracy so that we can update the weights, that is called as backpropagation. We'll understand backpropagation in more detail. So let us move forward and understand what exactly is backpropagation. So what is backpropagation? Now let us understand this with an example. So we'll take the inputs as the leads generated from various sources. And my aim is to classify the leads on the basis of the priority. So there might be certain leads which won't make that much difference to me, whereas compared to the other leads. So in that case, I need to make sure the leads which are important gets the highest amount of weight. How am I going to do that? First, we'll see the output. Then accordingly, we'll calculate the error. And based on that error, we are going to update the weight. And this process is nothing but your backpropagation in a nutshell, I can say, right? Although the algorithm is pretty complex, but yeah, this is basically what happens. So in order to classify the leads on the basis of priorities, we need to provide the maximum weight to the most important lead. And how are we going to do that? We're going to compare the actual output and the desired output, and according to the difference, we're going to update the weights. So what is backpropagation? So backpropagation is nothing but a supervised learning algorithm for multi-layer perceptron. Now let us understand what exactly is this algorithm. Let us understand this with an example that is there in front of your screen. So these two are our input neurons, these two are our hidden neurons, and these two are our output neurons. Now our aim is to get 0.01 and 0.99 as our output. And at the same time, we have inputs as 0.05 and 0.10. Initially, we take the weights as we can see it here. So 0.15 W1, 0.20 W2. So these are the weights. Plus we have two biases as well. Now what we need to do is we need to make sure that we have weights in such a way that we get output as 0.01 and 0.99. But let us see if we get that same output when we provide these kind of weights. The net input for this particular H1 will be what? It'll be W1 into I1, that is the first input, plus W2 into I2 plus B1 into 1, which gives us the answer as 0.3775. Similarly, the output for H1 will be nothing but the activation function, the output after the activation function. And we are using here sigmoid function because our brain also uses a sigmoid functions. That's what we believe in. And at the same time, it is easily differentiable. And if you differentiate it twice, you get the same number. So the output of H1 will be 0.59 something. So let me go back. So the output of this particular H1 will be 0.59 something. Then we're going to calculate the output of H2 as well similarly. And we get the output as 0.5968884378. Next up, we are going to repeat the process for the output layer neurons as well. So for the output layer, the net input will be W5 into out of H1, W6 into out of H2 plus B2, that is the bias. So we get the output somewhere like this. And then the net output for out O1 will be after the activation function, which will be 0.751. Similarly, the output for O2 will be 0.77. Now, if you notice that this is not the desired output. Our desired output was 0.01 and 0.99. What we got instead, we got 0.75 and 0.77. So what we need to do, we need to update the weight. So for that, we're going to calculate the error. Now, error for output O1 is nothing but the sigma of 1 by 2 target minus output whole square. Target is nothing but your desired output and output is your actual output. So your error of output of O1 neuron will be 0.278. Similarly, for O2 will be 0.023. So the total error comes down to 0.29 something. Next up, we need to update the weight so as to decrease this error. Now what we're going to do, we're going to first calculate the change in total error with respect to any of the random weight. We'll take W5 for example, just to show you. So we're going to calculate the change in the total error when we change with respect to the weight W5. So we're going to apply a chain rule here. So using partial derivative, we're going to calculate E total by delta of out O1 into delta of out O1 by delta of net O1 and then delta of net O1 by delta of W5. As you can see it from this particular example as well. E total, change in E total with respect to out O1, change in out O1 with respect to net O1 and change in net O1 with respect to W5. We're going to multiply that and we're going to get this particular term. And let us see how we do that. So how much the total error change with respect to the output? E total by E out 1, we're going to calculate it. It came around 0.741. Similarly, we're going to calculate how much does the output O1 change with respect to the net output. And we get this. After that, we're going to calculate it for net output change with respect to W5 also, we got this. And then finally what we did, we put all these values together and we found out the change in the error with respect to the change in weight W5, which came to up around 0.082167041. Now is the time to update the weight. So how are we going to update the weight? First thing we need to do is we need to follow this formula. So W5 plus is nothing but the updated weight, which is equal to W5 minus the learning rate into delta of E total by delta of W5. So which came to around 0.35891648. Similarly, we can calculate the other weights as well. So we're going to repeat the same process and we're going to calculate the other weights as well. Then again, we're going to see how much is the loss. If still the loss prevails, then we're going to repeat the same backpropagation learning algorithm again for all the weights. So this process will keep on repeating. So this is how backpropagation actually works. So we'll actually have a separate module in which we'll discuss backpropagation in much more detail. So now what I'm going to do, I'm going to make use of the same MNIST data set and I'm going to increase the efficiency of that data set by 97 to 99% with the help of multi-layer perceptron. So guys, let us go ahead with that. So guys, as I've told you earlier as well, we are going to use the same MNIST data set which we have used in the single layer perceptron. So I'm going to perform a classification using multi-layer convolutional networks. Now what are convolutional networks? Basically these networks are used in order to classify images. We have a separate module on convolutional networks, so you don't need to worry about it right now. So basically what I'm doing is I'm just trying to show you
that how we can increase the efficiency using the convolutional neural networks. I'm just giving you a general overview, or you can say a taste of how things work in convolutional neural networks. So we give an input image to this convolutional network. Then this input image is processed in the first convolutional layer using the filter weights. Now this result in 16 new images, one for each filter in the convolutional layer. The images are also downsampled, so the image resolution is decreased from 28 cross 28 to 14 cross 14. Now these 16 smaller images from the first convolutional layer are then processed in the second convolutional layer. We need filter weights for each of these 16 channels, and we need filter weights for each output channel of this layer. Now there are total 36 output channels, so there are total of 16 cross 36 equal to around 576 filters in the second convolutional layer. Now the resulting images are downsampled again to 7 cross 7 pixels. The output of the second convolutional layer is 36 images of 7 cross 7 pixels each. Now these are then flattened to a single vector of length 7 cross 7 cross 36, which is a 1764. Which is used as the input to a fully connected layer with 128 neurons. And this feeds into another fully connected layer with 10 neurons, one for each of the classes, which is used to determine the class of the image, that is, which number is depicted in the image. So whatever number that we provide in, so basically the output layer, or you can say the last layer or the fully connected layer with 10 neurons is used to determine the class or which digit is the input image of. Now the input image depicts the number 7, and the 4 copies of the images are shown here. So basically what happens, whatever filter we have in each layer, it will be present on the image pixels. So there will be a dot product of the filter and the image pixel behind that. So we'll get a dot product there. We are going to repeat that same process in each of these layers, and for each of these layers and for each of these images. And we are calculating the dot product. So I hope you get the point. And you don't need to worry about it if you're not able to understand this concept right now, because we haven't talked about convolutional neural networks at all. So let me just show you that we can increase the efficiency. So I've already run the code, and it will take time if I do it right now. So this is what the efficiency we ended up with. So it is 98.8%. So on the test sets, we had around 10,000 test samples, out of which we predicted 9,876 correctly. So which is pretty good actually, if you see. So because in the single layer perceptron example that we took, we were getting accuracy of around 92%. But here we are getting around 99%, which is actually very good. All right. So this is all for today's session, guys. Thank you and have a great day.